Hi guys. All right. So the next topic we're going to cover is graphing polar curves. So last time we learned how to plot points, how to convert between rectangular and polar. Now we're going to graph polar curves. You can think of these as polar functions. So let's start with circles. Okay, the first type of graphs we're going to learn are circles. So circles will be of the form r equals either some sort of constant times sine theta, or r equals some sort of constant times cosine theta. Okay? If it's, well, we're going to come up with some characteristics and then together, okay, and so leave some space here. So let's try to discover those together. All right, so let's try an example. Example 1. Let's start with graphing r equals sine theta. So our a value, our constant in front, is 1. Okay, in rectangular form, let's say you're trying to graph y equals sine theta. Well, that graph looks like this, and we learned that last semester. We remember our critical points, our quarter points, midpoints, and all those. Our max is 1, minimum is -1. Okay, so in polar form, so this is rectangular. In polar form, our graph looks like a bunch of rings, right? Or our graph paper, I guess, our plane. And we use the points r theta to plot. So our input is the angle and our output is the r value. So then for r equals sine theta, we can start with the point 0, 0. Okay. Then we move on to pi over 2, 1. So in rectangular form, it's pi over 2, 1. In polar form, if we had to graph that coordinate, we'd go angle first. So pi over 2 first. And then we would plot the point. Then pi 0, we graph angle first and back to 0. So the points are starting to overlap. Okay, same thing for 3 pi over 2, -1. That kind of just flips back to where pi over 2, 1 is. So we get these doubles, these repeating points, right? 2 pi, you're back at 0. Well, that information is not very helpful. But look at what happens in between the points. In between 0 and pi over 2, your output is getting larger and larger and larger. Okay, so it goes from being 0 to getting bigger and bigger and bigger and bigger and bigger and bigger. And then from pi to 0, it actually starts getting smaller and smaller and smaller. So what we end up with is a circle. Okay, so this circle has our radius. So this is a circle with radius 1/2. It has symmetry with respect to, we don't have a y-axis, so we're going to call it a vertical axis. Okay, so if you want to try this on decimals or a graphing calculator, you may. So I did that. So here is my decimals. So here is r equals sine theta. I just typed r equals sine theta, and then on the tools, I just made sure I hit polar, so not rectangular, but polar graph. And that way I can see kind of what that looks like. Okay. So if you want to play around, you can also try r equals cosine theta. And you see now we have a circle of radius 1/2 with symmetry with respect to the horizontal axis. So if you play around, you'll see r equals, let's try r equals, how do we make the radius bigger? So if the radius was a half, let's say I want a radius of 4. So then let's try a cosine theta. So that gives me a bigger circle with a radius of 4. Okay, so our radius is determined by our a value here. Okay, so then let's go back to the top. Okay, so what I was trying to get at was that if you have a sine, if it's going to be sine function, you're going to have symmetry with respect to vertical axis. If it's cosine, you're going to have symmetry with respect to horizontal axis. And if you remember from Desmos, this is what r equals cosine looks like. Okay, where the radius is half of the a value, and r equals a sine. It's more up there, where your r value, your radius, I mean, is a over 2. Okay, so then what else? So can we remember about these? So symmetry with the vertical axis. Remember, sine is an odd function, and cosine is an even function. So this is where these symmetries are coming from. Our radius for both of these is a over 2. Okay, and you can use a helper graph to help you figure out where you start and where you end. Okay, so let's try an example. Example 2. Let's graph r equals 10 cosine theta. So what I would do is I would start with a helper graph. My max is 10, my minimum is 10, 0 to 2 pi. Rectangular form, starts at max, equilibrium, minimum, equilibrium, maximum. And I would take that and graph it in polar form. So if my a value is 10, I'm going to need at least 5 rings. All right, so then at 0, actually 10 rings. Oh, well, okay, maybe this was a bad example, but we can rescale it. We can let each one of these rings stand for 2. So this is r equals 2, 4, 6, 8, 10. Okay, so then 0, 10, when my angle is 0, I'm going to plot at 10. Okay. When my angle is pi over 2, I'm back at 0. So I know that this is what my circle is going to look like. I know that my radius is 5 units. So that means that my circle, what would get me 5? Let's see, at pi over 3, maybe? Let's see, cosine of pi over 3 is a half. So 10 cosine pi over 3 is 5. So at pi over 3, here's pi over 3, I would go out 5 rings. 1, 2, 3, 4. Well, half, because I scaled it by 2. Let's pretend I did this nice and pretty. Okay, so this is what my circle looks like. So that's how I would graph one of these. And again, I'm not going to be super strict on, oh, it's not the perfect circle. I mean, obviously, I can't even draw a perfect circle here. So, oh, there it is, a perfect circle. But, whatever you do, I'm sure will be fine. And I'm going to do a lot of matching. So as long as you get the general idea of how this graph looks like and understand the symmetries, you're going to be fine.